My research work is Comparative Study, Synthesis, Characterization, ORR activity of PoT and Titanium PoT Nanocomposites. Introduction. Nanocomposites constitute a class of hybrid materials composed of a polymer matrix and an inorganic component which has at least one dimension in the nanometer. To improve and extend the functions of these inorganic nanomaterials, one or more components are often incorporated to form multifunctionalized nanocomposites for various applications in the field of electronic sensors, catalysis, energy, electromagnetic interference shieldings, electrohelical fluids, and biomedicine. Conducting polymer composites with nanostructures have attracted significant academic and technological attention because of their unique physical properties and potential applications in nanoelectronics, electromagnetic, and biomedical devices. Recently, the conducting polymers inorganic modified electrode is used for oxygen reduction reaction because the ORR is the main current producing cathodic process in fuel cell. Platinum electrodes were the first choice for the use in fuel cells, but their high cost has necessitated the researchers leading to preparation of low cost modified electrodes in which there is decreased oxygen reduction at lower potential. Hence, the current interest lies in the utilization of carbon-based modified electrodes and mediator. Over the last few years, the electrocatalysis of oxygen reduction on various conducting polymers, ceramic modified electrodes were studied. These materials are especially important owing to their bridging the world of conducting polymers and that of nanoparticles. Based on the importance of connecting polymer of orthotoluene was chosen as the monomer for the present research work. Chemical oxidative polymerization of the monomers was carried out by incorporation of ceramic titania into the polymer matrix. Nowadays, coated electrode or modified electrode systems are very much employed to characterize organic inorganic hybrid compounds. Objectives: to synthesize polymers of orthotoluene using potassium perdisulfate as the adsorbent. To synthesize ceramic incorporated polymer nanocomposites of orthotoluene. To investigate the spectral behavior, that is UV visible and FDR of polymer and polymer metal oxide nanocomposites. To determine the structural properties and particle size through XRD experiments. To study the surface morphological behavior using SEM and to confirm the incorporation of the metal oxide in the polymer matrix with the help of EDOX, to study the thermal behavior of polymer and polymer ceramic nanocomposites using thermoanalytical techniques, that is TGA and DTA, to find out the electrochemical behavior in modified electrode systems of the polymer and polymer ceramic nanocomposites, to study the effect of concentration, pH and effect of different atmospheric conditions, to find out the reduction behavior in methanol. These are the chemicals used to prepare polymer and polymer metal oxide nanocomposites. Synthesis. Synthesis of polymer. Actually, about 9 ml of orthotoluene and 13 gram of potassium perdisulfate, 1 mole of hydrochloric acid were made up to 200 ml using conductivity water. The solution was kept stirred for about 3 hours with the help of a magnetic stirrer at a room temperature. Then it was kept overnight in the refrigerator, after which the dark green powder was obtained and was filtered and dried. The solubility of PoT was tested and was found to be soluble in dimethyl sulfoxide and dimethyl formamide. Synthesis of PoT metal oxide nanocomposites. PoT metal oxide nanocomposite was synthesized by bulk polymerization of 9 ml orthotoluene monomer and 13 gram potassium perdisulfate, 0.25 gram titania and 6 ml of hydrochloric acid were made up to 200 ml. The solution was stirred for 3 hours to obtain a uniform suspension containing titania particles. The temperature of the nanocomposites was maintained at 0 degrees Celsius for 24 hours to complete the reaction. Then the obtained precipitate was filtered and washed with distilled water until the washings became colorless. The synthesized PoT TNS were dried at room temperature. Various amounts of titania were mixed with 0.1 molar orthotoluidine monomer to obtain PoT titania nanocomposites of varied composition of TiO2, which are designated as PoTT-NC1 to PoTT-NC6. The characterization of polymer and polymer metal oxide nanocomposites were studied using these instruments. These are the UV visible studies. Prepared polymer and polymer metal oxide nanocomposites were studied by UV visible spectroscopy. PoT depicted two absorption band, that is 262 and 462 nanometer. The first band indicate the substituted benzene due to polar group and pi-p conjugation interaction. The second band is attributed to pi-pi star transition and increases with the conjugation of polymer. The introduction of titania into polymer matrix, the pathochromic shift was observed, and also found that relative intensity, the peak alters with different content of titania, which shows that titania nanoparticles encapsulated by PoT chains tends to eliminate the interaction between the PoT chains, leading to dispersed polaron band. FTR spectra of PoTTNS and polymer have seen this figure. These characteristics indicate polymer, and these characteristics peaks also indicate as the polymer metal oxide nanocomposite. Specifically 616 per centimeter indicates titania oxygen titania symmetrical stretching frequency. X-ray diffraction patterns were recorded for polymer and polymer metal oxide nanocomposites. PoT peak shows 2 theta value 28 degree that exhibit an amorphous hump. XRD pattern of polymer metal oxide nanocomposites, the 2 theta values are exactly matched with anatase titania, and the broadening of first peak at about 24 to 29 degree was due to PoT. It clearly shows that titania nanoparticles has been encapsulated by PoT. PoTTNC1 peak is rather sharp, indicating more crystallinity and hence high conductivity. The average particle size is 26 to 62 nanometer using Serrer's formula. As a result of the above discussion, PoTTNC1 was specifically taken for the further studies. In this morphological studies, the TEM images shows that the dark spot clearly indicates titania nanoparticles is encapsulated by the PoT matrix. The thermal behavior were studied for both polymer and polymer metal oxide nanocomposite. This figure clearly indicates the polymer metal oxide nanocomposites. The thermal stability is very higher when compared to the polymer. Electrochemical studies. Polymer and polymer metal oxide nanocomposite modified glassy carbon electrode were employed in the electrochemical studies. 3 electrode cells, that is saturated calomel electrode, platinum wire, and polymer metal oxide modified glassy carbon electrode act as a working electrode. All electrochemical experiments were carried out at a thermostatic temperature of 27 degrees Celsius. Polymer and polymer ceramic nanocomposite films were produced by casting the solutions 1 drop onto a clean and pre-treated GCE and then allowing the solvent to evaporate. They were consequently rinsed with water and then transferred to an electrochemical cell for experimental purpose. Conducting polymer and conducting polymer ceramic nanocomposite modified glassy carbon electrode. Cyclic voltometric studies of polymer and polymer ceramic nanocomposite modified GCE were performed for different pH concentration and atmospheric conditions. The CVs were recorded in 1 molar sulfuric acid electrolyte by casting the nanocomposite on GC working electrode and scanned between -1.2 to 1.2 volt at scan rates between 50 to 500 millivolt per second. Cyclic voltometric response was studied for different concentration of titania and polymer, that is PoTTNCS. The high peak current appeared for PoTTNC1. These results clearly indicate Potential increases with increasing the titania content as charge is directly related to the titania content. Effect of pH on the voltometric response was studied over the pH range 1 to 13. The optimum pH range for good sensitivity response appeared to be pH 1 for both PoT and PoT titania nanocomposites. The effect of different atmospheres, that is oxygen and nitrogen atmosphere, were studied. This study suggests that PoT modified GCE slightly enhances the electrocatalytic activity at the nitrogen and oxygen saturated buffer. In case of PoT and C1, that is the current density corresponding to the redox peaks is significantly lower at low potential, at the reduction peak shifted towards more negative, which indicate enhancement in the ORR activity. The effect of scan rate ran from 50 millivolt to 500 millivolt per second. This shows that the PoT and PoT titanium nanocomposite shows the adherent behavior. From the plot of logarithmic peak current against logarithm of scan rate, these two experimental slope values shows higher than the theoretical value of 0.5, which suggests that the process is absorption controlled. Linear sweep voltometric studies have been recorded in the presence of acidic methanol. The ORR activity are enhanced by nitrogen saturated buffer for PoT, but oxygen saturated buffer only enhanced by the ORR activity for PoTT and C1. Methanol reduction mechanism is shown here. Conclusion. Intrinsically conducting polymer and polymer metal oxide nanocomposites were synthesized along with oxidizing agent ammonium perdisulfate by bulk polymerization method with varying concentration of metal oxides. UV visible and FTR spectra confirm the formation of polymer and polymer ceramic nanocomposites. Polymer and polymer ceramic nanocomposites are in nanoscale, which are confirmed by XRD and TEM. Polymer ceramic nanocomposites are higher thermal stability than polymer. The electrocatalytic oxygen reduction ability is maximum for PoTT and C1 modified GC at pH 1 as well as acidic methanol in oxygen saturated buffer solution. The salient feature about this investigation is fossil routes for the synthesis and characterization of polymer and polymer ceramic nanocomposites, good thermal stability, enhanced electrocatalytic reduction behavior. Thank you.